think about how seamlessly our devices now interact, you know?
Mm-hmm.
Your smart speaker playing music, your car adjusting the AC.
Yeah, even your pet feeder knowing when it's dinner time.
Exactly. This whole interconnected world runs on the Internet of Things, or IoT. And well, if you're like us, you want to understand the magic behind it, but maybe without getting totally lost in the weeds, the technical details.
Right. You want the core idea.
Yeah. So consider this our shortcut, our way to get a solid grip on what actually makes IoT tick.
And we've really immersed ourselves in a ton of information here, looking at everything from how these devices basically talk to each other all the way up to the big systems managing these huge networks. Our goal today, pull out those key insights, so you walk away with a clear picture of the IoT engine room, so to speak.
Precisely. And we've sort of broken it down into 4 main areas to help make sense of it all.
Okay.
First, there's communication and processing the real back and forth that powers it. Then we looked at edge computing, analytics, and security, which is obviously huge.
Crucial, yeah. After that, the devices themselves, what's inside them, how they actually work, and finally the cloud platforms, how they manage everything, and, the challenges of scaling up. Sounds like a good roadmap. Okay, let's unpack this. Starting with the absolute basics. How do these devices actually talk to each other?
Right. So at its core, IoT relies on this constant data exchange. And that exchange needs rules. That's where communication protocols come in.
Protocols, okay.
Think of them like an agreed-upon language or maybe grammar for machines. They define how information is formatted, sent, received, basically ensuring everyone's on the same page.
Gotcha. Like a shared language. And our sources highlighted a couple of interesting examples. One was MQTT, Message Queuing Telemetry Transport.
Yes, MQTT. What's really key about MQTT is its efficiency. It's designed for devices that don't have a lot of power or bandwidth, like tiny sensors.
Lightweight, then.
Exactly. It uses this publish-subscribe model. Devices send out messages on specific topics, and other devices subscribe just to the topics they care about. Oh, okay. So it's targeted, like only getting news alerts for topics you actually follow, not just everything.
Precisely. Very efficient, doesn't waste bandwidth, sending data where it's not needed.
Makes sense. Another one mentioned was CoAP Constrained Application Protocol. How does that fit in?
Well, CoAP is also built for these constrained devices, low-power ones, but its approach is a bit different. It's designed to speak a language that's closer to the web protocols most people know, like HTTP. The significant thing is that it's made to be easily translated to HTTP. So imagine like a translator helping these tiny devices talk to the wider web. Much smoother integration.
Ah, okay. That makes a lot of sense for bridging the gap between, the tiny IoT world and the regular internet.
Yeah.
Our sources also mentioned some others, like standard HTTP and HTTPS, which people probably recognize, and Zigbee and Bluetooth Low Energy, BLE.
Right, exactly. HTTP, TTPS, you'll often see those used by IoT devices that have a bit more processing power, maybe needing direct web server interaction. And Zigbee and BLE, those are more for short-range wireless stuff. Think connections within your smart home or, between your fitness tracker and your phone. Personal networks.
So it's like a whole toolkit of different languages, really.
Right.
Each suited for a different kind of job, a different kind of conversation.
That's a good way to put it.
All right, so once these devices are all chattering away using these protocols, what happens to all that data? There must be a ton of it. Real-time data processing sounds like it would be absolutely essential here.
Oh, it's critical. Absolutely. In so many IoT applications, the value of data just drops off really quickly. You need to process it now.
Right.
Processing it immediately as it arrives lets you take quick action, makes everything run much more efficiently. Think about traffic updates. Knowing the traffic right now is useful. An hour ago, not so much.
Yeah, good point. Can you give us a clear example of why that immediacy is so important?
Well, okay, take immediate decision-making. Imagine a sensor in a factory. It detects a machine is overheating, like a critical temperature spike.
Yep.
Real-time processing can instantly trigger an alert, or maybe even automatically shut down that machine. It prevents a potentially massive, costly breakdown. That quick analysis leads to a direct, timely action.
Wow, yeah. Preventing that whole domino effect. That's powerful.
Yeah.
What about the impact on just, overall system efficiency?
Right. So by analyzing data as it's generated, systems can actually adjust themselves on the fly, dynamically.
How so?
Like a smart city's traffic system. It could analyze real-time traffic flow from sensors and automatically change the traffic light timings to ease congestion. It's about being constantly adaptive to what's happening right now.
So the system becomes kind of intelligent, self-optimizing in the moment.
Exactly.
Our sources also mentioned a few other benefits, like a better user experience, the instant feedback you get from a smart thermostat adjusting, and predictive maintenance, which sounds huge for industries, being able to see a failure before it happens.
Definitely. Big in industrial IoT.
And even better security, like detecting weird activity right away.
Yeah, all of those really stem from that immediate insight. It lets you be proactive instead of just reacting after something breaks. Saves time, money, headaches.
Definitely sounds like the way to go. Now, to push performance even further, we looked into something called edge computing. This seems to be about moving the processing closer to where the data actually comes from, like right near the devices.
That's the core idea, yeah. Instead of sending all the raw data across the network to some distant cloud server for processing.
Which could take time.
Right. Edge computing does some of that number crunching, maybe filtering, right there at or near the source, the IoT devices themselves, or a local gateway. Think of it like distributing mini brains throughout the network.
Mini brains, I like that. Okay, so why do this?
Yeah.
What are the big advantages of adding this edge layer?
Well, one huge advantage is reduced latency. Big time.
Latency meaning the delay.
Exactly, the time lag. By processing data locally, close to the device, you slash the time it takes for data to travel to the cloud and back. This near-instant response is absolutely critical for things like autonomous cars or robotic arms on an assembly line. Milliseconds matter there.
Yeah, you can't have lag when a car needs to brake instantly. Makes sense. What's another big win for Edge?
Enhanced data security is another major benefit. Think about it. If you process data locally, less sensitive information actually needs to be sent over the network to the cloud.
Ah, right.
You're keeping more data closer to home, under tighter control, potentially, fewer points of attack, less risk of interception during transit.
So keeping it local can actually make it safer.
Interesting.
The sources also mentioned lower bandwidth usage, which makes sense if you're filtering data locally, sending less stuff.
Yep, less network traffic.
Improved reliability, too, because a device might still be able to function, do its local processing, even if the internet connection drops temporarily.
That's a big one for resilience, yeah.
And also scalability and flexibility were highlighted.
Right. Edge computing helps distribute the load. It makes the whole system less fragile, less dependent on that single cloud connection, which helps when you need to scale up or adapt the system later.
Okay, so lots of good reasons for Edge. Now, all this data, whether it's processed at the edge in the cloud, eventually needs to mean something, right? It needs to be useful. That sounds like where data analytics comes in.
Precisely. Raw IoT data on its own is often just noise, a flood of numbers. Data analytics is the process of actually examining that data, interpreting it, looking for patterns, relationships, finding the valuable insights hidden inside.
So turning noise into signals.
Exactly, turning raw info into actionable intelligence.
How does that actually help people using IoT? What are the practical benefits?
Well, a major one is just better decision-making, dramatically better. By analyzing IoT data, businesses, or even individuals can understand their operations or customer behavior or market trends much more clearly. This leads to smarter strategic choices, better resource allocation, just making things run better overall. For example, think about farming. Analyzing sensor data from fields can tell a farmer exactly when and where to water or fertilize. Better yields, less waste.
Right, data-driven farming, that's a concrete example. And predictive maintenance came up again here under analytics.
Absolutely. It's a prime example of analytics in action. By analyzing historical data and real-time sensor readings from machines, you can spot these subtle patterns that might indicate an upcoming failure. Maybe a slight increase in vibration or temperature over time.
Before it actually breaks down.
Exactly. Allows for proactive maintenance. Fix it before it breaks. That prevents costly downtime, extends the equipment life.
Yeah.
Hugely valuable in manufacturing, transportation, energy, anywhere. Equipment failure is a big deal.
Yeah, I can see that. Downtime costs a fortune. We also saw mentions of enhanced customer experience, like using data to offer more personalized services.
Right. Understanding user preferences better.
And operational efficiency, streamlining processes based on data, and also real-time monitoring and alerts, especially in critical areas like healthcare or, say, energy grid management.
Yeah, all these benefits really highlight how analytics unlocks the actual value in all that IoT data being collected. It's the key, really.
Okay, this is making sense. But with all these devices talking, sharing data, being analyzed, security has got to be a massive concern. We looked at IoT security protocols. What are the basic ways these protocols keep things safe?
Oh, absolutely essential. Top priority. IoT security protocols are all about protecting the confidentiality, keeping data secret, the integrity, making sure data isn't tampered with, and the availability, ensuring the system is actually usable, protecting both the data and the devices.
Okay, so confidentiality, integrity, availability, how do protocols achieve that?
Well, one fundamental method is data encryption. Think of it like scrambling the data using complex math, turning it into an unreadable code.
Like a secret digital lock.
Exactly. Only someone with the right key can unlock it and read the original information. This protects data, both when it's being sent over the network and when it's stored somewhere.
Makes sense. Sending messages in code. What's another key security layer?
Authentication and access control. These are like the digital bouncers or gatekeepers.
Right.
They verify the identity of users or other devices trying to access the system or data. This might involve passwords, maybe biometrics like fingerprints, or digital certificates, which are like electronic ID cards for devices.
So proving you are who you say you are before you get in.
Precisely. It prevents unauthorized access and controls who can do what within the system. Very important.
Okay, encryption and authentication. What's a third crucial aspect?
Secure firmware updates. This is really important. Firmware is that low-level software embedded right into the device's hardware, ensuring that updates to this firmware come only from trusted, verified sources and are installed securely is vital. It prevents attackers from loading malicious software onto the device, maybe to take it over or use it to attack other systems. You need to patch those vulnerabilities.
Right, so keeping the core software of the device safe and updated is a major line of defense. Our sources also mention things like data integrity checks, making sure data hasn't been altered accidentally or maliciously.
Yes, like a digital checksum or signature.
And also network security management stuff like firewalls, intrusion detection systems, and using the secure versions of communication protocols we talked about earlier, like HTTPS or MQTT with security layers added.
Exactly. It's all about layers. Building a defense-in-depth strategy. You need multiple layers working together to create a trustworthy IoT environment.
Okay, that makes sense. Layers of protection. Let's shift gears a bit now and look at the actual devices, the things in the Internet of Things. Sensors seem to be at the heart of many of them. What's their basic job?
Sensors are really the senses of the IoT world. They are the components that gather data from the physical environment.
Eyes and ears.
Eyes, ears, nose, skin, you name it. They detect changes, temperature, light, motion, pressure, whatever it is, and convert those physical changes into electronic signals that the device can then process or send out. They bridge the physical and digital worlds.
Got it. The physical to digital interface. What are some really common types of sensors we might encounter?
Oh, loads. But two very common ones are temperature sensors, pretty self-explanatory, measuring heat or cold.
Right, in thermostats, weather stations.
Exactly. And motion sensors, which detect physical movement. You find those everywhere, from home security systems to automatic lights.
Yeah, makes sense. Simple but widely used. The sources also listed others like proximity sensors detecting nearby objects without touching.
Yep, like in smartphones when you put it to your ear, or in parking sensors on cars.
Humidity sensors for moisture in the air, and pressure sensors used in weather forecasting or even tire pressure monitoring in cars.
Right. It just shows the huge variety of data points that IoT can capture about the real world. The specific sensor just depends entirely on what you need to measure for that particular application.
Okay. Now, these devices aren't just static hardware, are they? They have software, firmware, and that needs updating. Why are software updates so important for IoT devices?
Oh, hugely important. Ongoing updates are critical for several reasons. Probably the most important one is security enhancements.
Back to security again?
Always back to security.
Yeah.
New vulnerabilities are found all the time. Updates deliver the patches, the fixes for these security holes. They're essential to protect devices from evolving cyber threats. Think of them like digital immune system boosters.
Keeping the defenses up to date. Good analogy. What's another key reason for updates?
Bug fixes and performance improvements. Software isn't always perfect first time around. Updates fix glitches, errors, inefficiencies that might make a device crash or run slowly or drain its battery too fast. They keep things running smoothly and reliably.
Yeah, nobody wants a buggy smart device. Reliability is key. Our sources also mention that updates can actually introduce new features and functionality over time.
Right. Make the device better or add new capabilities.
And also ensure compatibility, making sure devices work well with newer systems or other devices, and sometimes even regulatory compliance, keeping devices up to code with changing rules.
Exactly. So it's not just about fixing things. It's about maintaining security, performance, compatibility, and even adding value over the device's lifespan. Regular updates are just part of the deal with connected devices.
Okay. Now, all these devices, sensors, processors, they all need power to run. How do IoT devices actually get their juice? Must be quite varied.
It is very varied, yeah. The power source choice really depends on the device, its function, where it's located. Batteries are obviously super common.
Right.
They offer portability, flexibility. You get rechargeable ones like the lithium-ion batteries in your phone or wearable tech, often optimized for long life and efficiency. And non-rechargeable ones, too, for very low-power devices designed to last years without intervention.
Okay, batteries make sense for a lot of things. What about more, maybe sustainable or hands-off options?
Yeah, energy harvesting is a really interesting and growing area. This is where devices literally collect energy from their surroundings.
Like how?
From sunlight using tiny solar panels, from heat differences using thermoelectric generators, from vibrations or movement using kinetic harvesters, even from ambient radio waves like Wi-Fi signals.
Wow, pulling power out of the air almost.
Kind of. It's fantastic for remote deployments. Think environmental sensors out in a field, or structural monitors on a bridge where changing batteries is impractical or really expensive. The goal is often a device that can power itself indefinitely.
That does sound like the future. Very cool. What's another common way devices get power?
Power over Ethernet, or PoE, is pretty common, especially for network devices.
Oh, okay, PoE.
Yeah, this lets devices like, say, IP security cameras or Wi-Fi access points get both their electrical power and their data connection through the same standard Ethernet cable.
Ah, convenient. One cable does both jobs.
Exactly. Simplifies installation a lot. No need for a separate power outlet near the device.
Makes sense for things plugged into the network anyway. Our source has also mentioned just direct power supply, plugging into the wall with an AC/DC adapter for stationary things like smart hubs or appliances.
Yep, standard way for things that don't move.
And wireless charging, which we see more with wearables, phones, even some medical devices now. No need for physical connectors.
Right, becoming more popular for convenience. So yeah, a whole spectrum of power solutions really driven by the device's needs, size, location, power consumption, lifespan.
It's clearly a key design choice. Okay, let's zoom out again, look at the bigger picture. All this data from all these devices, a lot of it ends up in the cloud, right? These IoT cloud platforms sound like central command centers. What do they do in terms of processing the data?
They're definitely central hubs, yeah. Built to handle the scale of IoT. One core feature, as we mentioned, is real-time data processing. These platforms are designed to ingest and process potentially massive streams of data arriving simultaneously from millions of devices.
So handling that immediate processing, but at a massive scale in the cloud.
Exactly, orchestrating it. Another key thing they do is data aggregation and filtering.
Meaning?
Well, they collect data from all sorts of different devices, pull it together into more unified data sets, and importantly, filter out the noise, irrelevant data, duplicate readings, errors. It's like cleaning and organizing the data flood, making it ready for analysis.
Okay, kind of like data janitors tidying everything up.
Yeah, a bit like that. Sophisticated janitors.
Our sources also pointed to, obviously, data storage and management. You need somewhere to put all this data, and it needs to scale.
Absolutely. Huge storage needs.
Plus, advanced analytics and machine learning tools often built right into the platform, and data visualization tools to actually see the patterns and insights in a way humans can understand.
Right. Dashboards, charts, reports, making the data accessible. So yeah, the cloud platform really acts as the central brain and nervous system for managing and extracting value from all that IoT data.
Makes sense. Now, if you have potentially millions or even billions of these devices out there, managing them must be a nightmare. How does that work? What are the key device management functions?
Yeah, managing that fleet is a huge challenge, and dedicated management systems are crucial. One basic function is device provisioning and onboarding.
And provisioning.
It's the whole process of getting a new device set up and securely registered onto the network for the first time, making sure it's recognized, authenticated, and configured correctly so it can start sending data and be managed properly, like an official enrollment.
Okay, a secure welcome process for every new device. Got it. What else is critical for management?
Device monitoring and diagnostics. Absolutely vital. These platforms constantly track the health, status, and performance of all the connected devices.
Like a health dashboard.
It's exactly. Looking for malfunctions, connection issues, errors, performance dips. And when something goes wrong, diagnostic tools help figure out why, so it can be fixed quickly, hopefully remotely. Minimizing downtime is key.
Keeping an eye on everything, making sure it's all working properly. The sources also mentioned deploying those firmware and software updates remotely, which we already talked about, being important.
Right, managing those updates across thousands or millions of devices centrally.
And security management, enforcing security rules, maybe remotely locking or wiping a device if it's compromised.
Central security hygiene, yeah.
And also device configuration and control, being able to tweak settings or send commands to devices remotely.
Right, adjusting parameters, turning things on or off. So yeah, it's a powerful, centralized control panel for the whole IoT deployment. Without effective device management, large-scale IoT would just fall apart. It'd be chaos.
I can imagine. Okay, final big topic, scalability. As these systems grow, adding more and more devices, more data, what makes or breaks an IoT system's ability to scale up effectively?
Scalability is a huge consideration, and several factors play into it. One really fundamental one is the network infrastructure itself.
The pipes, basically.
Yeah, the pipes need to handle the flow. As you add more devices and data volume explodes, the network, whether it's Wi-Fi, cellular, LoRaWAN, whatever, needs enough capacity, enough bandwidth, and low enough latency to handle all that traffic without grinding to a halt.
So the network has to be ready for growth. What else?
Device interoperability is another big one,
Yeah.
super critical.
Interoperability, meaning devices playing nicely together.
Exactly. IoT ecosystems often mix devices from different manufacturers using different technologies. For the system to scale smoothly, these different devices need to be able to communicate and work together. Usually this relies on using open standards and protocols so they speak a common language.
Back to those protocols again, ensuring everyone can talk to each other, even if they're from different families.
Precisely. Avoids getting locked into one vendor and makes adding new different devices much easier.
Okay, network capacity, interoperability. What's a third key factor for scaling?
Data processing and storage capabilities are obviously huge. We talked about the cloud. As data volumes balloon, you need back-end systems, cloud platforms, maybe edge computing nodes too that can scale up their processing power and storage capacity to handle it all without getting overwhelmed.
Right, the back end needs to grow along with the front end devices.
Definitely. You need that elastic capacity, especially in the cloud, combined perhaps with edge processing to manage the load effectively and, ideally, cost-effectively.
Makes perfect sense. Our sources also flagged security and privacy, saying they get way more complex as you scale up.
Oh, absolutely. More devices mean a larger attack surface. More data means more privacy risk. Security needs to scale too.
And power management, managing power efficiently across potentially thousands or millions of battery-powered devices becomes a much bigger logistical challenge at scale.
Very true. All these things are interconnected. Scaling IoT successfully requires thinking about the network, the devices, the data, security, power, the whole picture right from the start.
Wow. Okay. So we've really covered a lot of ground today, haven't we?
We definitely have.
We dug into how these devices talk using communication protocols, why processing data in real time is so vital, how edge computing boosts performance.
Right, and how analytics turns all that data into actual insights, plus the crucial role of security protocols.
Yeah, and then the devices themselves, the sensors gathering data, the need for software updates, the different ways they get power.
And finally, the cloud platforms managing the data and devices, and the big challenge of making it all scale up.
It feels like understanding these different layers, communication, processing, security, devices, cloud, scalability, really gives you a solid foundation for understanding IoT.
Absolutely. It moves you past just the buzzwords, you know. You start to see the essential building blocks, the mechanics of how this technology actually works and impacts our lives and industries.
And hopefully that gets us back to our original goal, helping everyone get a good handle on this important topic efficiently without feeling like they need an engineering degree. Hopefully this deep dive provided that kind of shortcut.
I hope so too.
So thinking about all these building blocks we've discussed, it makes you wonder, doesn't it? What new possibilities or maybe what new challenges might emerge as IoT keeps evolving and weaving itself even deeper into our daily lives, into our industries?
That's a great question to ponder.
Yeah, definitely something interesting to think about, maybe explore further based on what caught your interest today.
It's certainly a field that's not standing still. The foundations we talked about are key, but the learning and discovery journey in technology like this is definitely ongoing.